Alright guys, so in this video we're going to look at forces of pull or push, FPs, applied at an angle. Alright, so I want you to write down, pause the video and write down this problem in your notebook, and then I'll walk you through how to solve for it. Okay, so pause it now. Alright, so now that we're back, what we're doing, we're trying to find a sled is pulled at an angle with a force of 1,000 newtons and 30 degrees upwards, okay, from the horizontal. And they give you the coefficient of friction, and we want to solve for acceleration is our unknown. So really what we're going to be solving for is AX, the acceleration, the X direction. Our coefficient is 0.8 we could list. Our force of pull is 1,000 newtons, and our angle is 30 degrees. The other thing we know is the mass of the sled is 90 kilograms. All right, so you could list your givens, and then we will start our problem. Remember, the first thing we do in our problem all the time is we draw our force diagram, okay? It's gonna look a little different than the ones we've been drawing. Just one small difference. There still is, we're on Earth, so we have gravity pulling us down. We still have the ground beneath the sled pushing up with a normal force. We still have, as it slides along the ground, the sled experiences a frictional force, all right? And there's a pull force, but now that pull force is upwards at an angle there. Instead of completely horizontal, it's up a little bit. And it's above the horizontal by 30 degrees. So draw your force diagram like that, all right? The next thing we're gonna do is we're gonna split our forces into split our force of pull into X and Y components, okay? If you remember, the pull was not in the X or the Y direction. It was kind of in between. So we need to say how much of that pull goes in the X and how much goes in the Y. So we're going to redraw our force diagram, and this is how to do it. You want to keep the Fn, the Ff, and the Fg the way they were, because those were already either in the X or the Y direction completely. But the pull, which was at upwards at an angle, we're going to split that and make it look like a triangle, where Fpx, which is the part of the pull that goes in the X direction, and we're going to split it into Fpy as well, which is the part of the pull that goes upwards or in the Y direction. All right, and you could put 30 degrees there. Now, if you notice, the Fpx is the adjacent leg of the triangle to the 30 degrees. And the y is opposite of the 30 degrees, the Fpy. All right, so write the A and the O there. All right, so Fpx is going to be equal to the pull, all right, multiplied by the cosine of 30, because it's adjacent. And Fpy, all right, is going to be equal to our Fp multiplied by the sine of 30, because it's opposite. All right, remember, SOHCAHTOA. You can write that at the top of the page. Sine is opposite over hypotenuse, so we have our hypotenuse, which is the Fp. And cosine is adjacent over hypotenuse. So we'll use cosine to get the x, or the adjacent, to the 30 degrees, and sine to get the opposite, all right? So now let's do our final force diagram. Here I just showed you how to split the components, split Fp into components. Our final force diagram will have everything either in the X or the Y direction, nothing at angles anymore. So Fg, Fn, and Ff still exist, but Now FP has a y and an x part, and it's split up into each of those parts. All right, so and for FPY, really instead of writing FPY, you could write FP sine 30, and for FPX, instead of writing that, you could write FP cosine 30. All right. So if you multiply your pull force by cosine in our example, you could get the x component of the pull. And if you multiply our pull by sine of our angle, you could get the y part of the pull. All right, and that's your final force diagram for an object pulled at an angle, upwards at an angle there. All right. Now, we're going to write our, just like we've been doing, once we have a force diagram, we're going to write our statement for F net x and F net y. All right, and we're going to use the diagram to do that. So let's start with the x. All right, so we'll do F net x equals FP cosine 30, that's the force that's going to the right, minus FF equals MAX, and AX is what we're going to solve for later. And then we can make the statement for the y. Now for the y direction, there are actually two upwards forces, so both of those are positive. Fn plus Fp sine 30 minus Fg equals MAY. All right. So those are your statements. You got your up forces, both of those, minus your down force, gravity, and you got your force to the right, Fp cosine 30, minus your force to the left, Ff. All right. So now we're going to use those statements to solve for acceleration. Which acceleration are we solving for? Ax. So if we look at our F net x statement, we're just trying to plug in and solve now. Fp cos 30, Ff. I'm going to just rewrite the statement for F net x and see if I have enough stuff to solve for the acceleration. Let's look back at our list of givens. Okay. And we could see that we know what Fp is, so we could plug that in. That's 1,000 newtons times the cosine of 30, don't forget that. We don't know what Ff is yet. We know the mass right here is 90 kilograms, so we could plug that in. So if we had friction, we'd be able to solve for Ax. So we gotta go find friction. Now we know the friction force we could find using this equation. Force of friction equals mu times Fn. And we are given mu in the problem. Mu is 0.8. So if we knew the normal force, we could multiply it by mu, get friction, put it up here, and solve for Ax. So once we find the normal force, we're ready to go. So you might expect normal force to be equal to force of gravity. And that has been true in the past, but it is no longer true now. You wrote out your F net y statement, and it looks a little different than it used to look when the force was not pulled at an angle. Because now there's a third term in the statement, Fp sine 30. Part of the pull is now in the y direction. All right. Now when you pull it, you don't lift it above the ground. So that means the AY is 0. So the right side of that equation is still 0. So let's plug in and solve for Fn. We could do 1,000 for the pull, sine 30. Don't forget that Fn and Fg are not balanced this time. Don't forget the Fp sine 30 in this statement. But we need to know what Fg is. That's pretty simple to figure out. Mass times gravity. Okay, so Fg is the 90 kilograms times 9.8. Now we're going to start calculating some things. 90 times 9.8 is 882. All right. And now you have enough stuff to plug in and solve for Fn. So Fn is going to equal, when we move this term over to the right side and the 882 to the right side, Fn will equal 1,000 sine 30 plus 882. Oh, you know what? I made a mistake here. Oop. Should that be minus there, right here? Let's go double check our F net y statement.